In October of 1973, over the burning desert of the Sinai Peninsula, one of the fiercest aerial engagements in human history unfolded without mercy. The skies transformed into a graveyard where modern Soviet air defense systems, supplied to Egypt and Syria, were plucking Israeli fighters from the heavens by the dozen. But this was no clean victory. For every Israeli aircraft that fell in a flaming arc toward the sand below, the Arab defenders paid a terrible price in attrition. Sophisticated Israeli electronic warfare equipment, cunning tactical innovations, and countermeasures that appeared like magic were turning the tide. In the war rooms of the Soviet General Staff, in the offices of military planners who had never doubted their systems, a profound and uncomfortable realization was crystallizing. The weapons that had dominated aerial combat just years before were becoming obsolete. The Egyptian and Syrian forces were winning battles, yes, they were destroying aircraft. They were inflicting casualties. But they were losing the race that actually mattered. The race against technology, the race against innovation. The race against enemies who were learning, adapting, and finding new ways to neutralize yesterday's miracles. Somewhere in the halls of power in Moscow, in late 1973, as battle reports filtered in from the Middle East, senior military officials gathered to confront an uncomfortable truth that would shape the next decade of weapons development. The missile systems they had deployed were being overwhelmed by electronic countermeasures. Within months, within a few years at most, Western nations would develop techniques and tactics that would render even the most advanced Soviet defenses vulnerable. A decision crystallized in those war rooms. They needed something revolutionary, something that could pierce through electronic fog, something that could see through deception, something that could identify and engage targets that no existing system could reliably detect. They needed a weapon of an entirely new generation, a system that would terrify the skies, a system that would make every NATO pilot think twice before climbing into his cockpit. By 1971, the Soviet Union had already fielded a system that was considered revolutionary for its time. It was called the OSA, or WASP in English. It was mobile. It could move across terrain with frightening speed. It was amphibious. It could wade through water and keep fighting. It was capable of hunting low-flying targets with an effectiveness that left Western military planners deeply troubled. Pilots who had trained to expect certain performance envelopes from their aircraft suddenly found themselves operating in an entirely new threat environment. The OSA changed everything. But the moment the first OSA rolled off the production line, the engineers who had designed it already knew it was becoming obsolete. They understood, with the terrible clarity that comes only from deep technical knowledge, that their magnificent creation would be dead within a decade. American military designers were working on entirely new generations of cruise missiles, weapons that could snake across the landscape at treetop height, following the contours of the terrain itself to evade detection, flying so low that radar operators would have difficulty separating the missile from ground clutter. These weapons were coming. It was inevitable. Reconnaissance drones were being developed, unmanned aircraft that could hover over Soviet strategic positions for hours, gathering intelligence with complete impunity. Soviet air defenses couldn't shoot at unmanned targets effectively because drones didn't carry enough explosive material to damage an air defense system significantly. And the fighter bombers, the tactical aircraft that NATO would deploy in the next generation, were becoming faster, more agile, more sophisticated with each passing year. Most troubling of all to Soviet planners, these aircraft were being equipped with electronic warfare systems that could render radar operators nearly blind. These electronic warfare systems didn't just jam radar. They created false targets. They created confusion. They manipulated the very signals that defenders relied upon to see threats. By the mid-1970s, Soviet military planners had reached a strategic conclusion that would shape a generation of weapons development. They understood with crystalline clarity that the next war, if it came, would not be won by superior pilots or superior tactics alone. It would be won by whoever possessed superior technology. Specifically, it would be won by whoever could maintain clarity in an electronically hostile environment. The warfare of the future would be a battle of signals, a battle fought at the speed of light, a battle where false images would be more valuable than real ones, a battle where the ability to see through deception would separate victory from defeat. In 1972, in the corridors of the Electromechanical Research Institute in Moscow, a word was spoken for the first time that would echo through the decades to come. That word was Tor. In English, it translates as thunder. It was meant to evoke something elemental, something primal, something unstoppable. The engineers who gathered in those corridors to discuss this new system knew the magnitude of the challenge before them. They had just completed the agonizing work of bringing the OSA to full maturity. They understood its weaknesses intimately. They knew where it could be jammed. They understood the limits of its reaction time. They recognized that it could not simultaneously handle multiple attacks from different directions. Its missile range was limited against fast-moving targets. Its fire control radar could be blinded by determined opponents. What they were about to propose was not a simple modernization. This was not about adding some new components to an existing design. What they were discussing was something far more ambitious. something revolutionary, a completely new architecture from the ground up, entirely new electronics, a new missile designed from first principles, a new doctrine of operation based on technologies that didn't yet exist in practical, combat-ready form. But there was a profound and seemingly insurmountable problem facing the engineers, who were beginning to sketch the outlines of this new system. The central technology they dreamed of didn't yet exist in the form they needed. The dream of the designers was a radar antenna with a phased array configuration. The Soviet Union had mastered this technology years earlier. It was proven, it was reliable, but those applications were enormous. The phased array radars that protected Soviet cities and strategic military installations occupied entire buildings. They were fixed in place. They consumed enormous amounts of electrical power. They were designed to be maintained by teams of specialists. To miniaturize this technology, to compress all of its sophistication into a compact form that could fit on top of an armored vehicle, was considered a task that bordered on the impossible. A phased array radar doesn't work by rotating an antenna. That's the key innovation. Traditional radars spin their antenna mechanically, round and round, searching the sky. A phased array radar steers its beam electronically. By adjusting the timing of signals sent to thousands of tiny elements in the antenna, the beam can be redirected instantaneously. No mechanical rotation, no precious seconds lost while the antenna completes its scan. The beam can jump from one target to another in microseconds. But this incredible capability comes at a terrible cost. The electronics required to control a phased array antenna are staggeringly complex. The computing power needed to manage the beam-forming calculations is immense. The reliability requirements are unforgiving. Every single element in the array has to work perfectly, or the entire system degrades. A single failure could cascade through the whole structure. For mid-1970s technology, creating a phased array radar small enough to fit on a vehicle seemed like a task that would take decades. But the designers weren't content with simply miniaturizing existing technology. They had a vision that went far beyond that. They didn't want separate vehicles for different functions. No detection truck here, no fire control truck there, no command post somewhere else, all connected by vulnerable cables snaking across the battlefield, all dependent on continuous line-of-sight communication. They envisioned something that had never been attempted before in a mobile, short-range air defense system. A single machine, one vehicle, that would detect targets, that would track targets, that would classify targets, that would aim, that would fire. All without external support, all without backup from other systems, all in complete autonomy. For the mid-1970s, this was not just ambitious, it was science fiction. It was the kind of thinking that could get a military officer labeled as unrealistic, as dreaming too much. But the Soviet military was desperate. They understood the trajectory of warfare better than anyone. Electronic warfare was going to dominate the next generation of conflict. The phased array radar, difficult as it would be to miniaturize, represented the one technological path that could address this new reality. In a moment of strategic vision, or perhaps desperation, the Soviet leadership made an audacious decision. They would take a pause, 3 years. They would grant the research institutes, the manufacturing plants, the test facilities 3 years to develop and mature the technologies that the designers were asking for. 3 years to make the impossible possible. 3 years to build the technological foundation upon which this revolutionary system could be constructed. During those 3 critical years, the Vietnam War continued thousands of miles away. Soviet intelligence officers collected every scrap of information they could obtain about how American aircraft were being defeated. Every downed American plane was studied. Every captured piece of electronic warfare equipment was analyzed in minute detail. Every intercepted radio signal, every radar transmission, every electronic command was cataloged and analyzed. This intelligence, this real-world data from actual combat, was fed back into the requirements for the Tor system. The engineers knew, with terrible clarity, exactly what they would be fighting against. And that knowledge made their requirements even more stringent. They knew what electronic warfare capabilities the Americans possessed. They understood what frequency bands the Western jamming equipment could operate in. They grasped the power levels, the bandwidth, the modulation techniques. This knowledge shaped every design decision that would follow. The Tor system would have to be resistant to jamming. It would have to be adaptable. It would have to be able to switch frequencies, to change its tactics, to defeat countermeasures that hadn't even been deployed yet. In early 1975, a formal decree issued by the Central Committee of the Communist Party of the Soviet Union gave official authorization for the work on the Tor system to begin. It was no longer a proposal. It was policy. It was a national priority. The machinery of the Soviet military-industrial complex was set in motion. They appointed a chief designer, a man named Veniamin Pavlovich Efremov. Efremov was not a young man. He was experienced. He had successfully designed the Krug air defense system years earlier, and the Krug was legendary in Soviet military circles. It had been tested in real combat. It had proven itself. It had the absolute trust of the troops who operated it. Efremov understood the weight of history. He understood that the system he was about to design would be in service for decades. It would be exported to allies around the world. It would define an entire generation of Soviet air defense technology. The responsibility was immense. Responsible for designing the vehicle itself, the chassis and suspension, and the mechanical integration of all the complex systems, they selected Iosif Matveyevich Dries. Dries, like Efremov, had cut his teeth on both the Krug and the OSA systems. He knew what worked. He knew what didn't. He understood, from painful experience, the terrible compromises required to squeeze complex, powerful systems into an armored chassis that still had to be mobile, still had to have adequate crew comfort, still had to be reliable in the field. And responsible for designing the missiles that would arm this revolutionary system, they chose the legendary design bureau known as Fakel, under the direction of Pyotr Dmitrievich Grushin. Grushin was a name spoken with reverence in Soviet military circles. His missiles had armed the S-125 air defense system. His designs had equipped the S-200 long-range air defense system. His missiles had traveled into battle on the backs of the Krug, the system that Efremov had designed. Grushin had the proven ability to design missiles that worked when the stakes were highest. Missiles that were reliable. Missiles that achieved their design specifications. Missiles that killed their targets. These three men, Efremov, Dries, and Grushin, and the teams of engineers beneath them, represented the absolute pinnacle of Soviet weapons design. They had decades of combined experience. They had the technical knowledge necessary to attempt the impossible. They had the institutional support of the highest levels of the Soviet military and political establishment. But even genius has its limits, and the challenges before them would prove to be extraordinary. Beyond the miniaturized phased array radar and the compact electronics that didn't yet exist, the designers wanted something that no short-range Soviet air defense system had ever attempted before. They wanted vertical launch capability. The missile would launch straight up from its container, reaching the apogee of its ballistic arc, and then, in midair, it would turn toward the target. This capability meant that the system could respond to threats coming from any direction without wasting precious seconds, rotating the turret to face the incoming threat. It meant the vehicle didn't need to maneuver into position. It could be attacked from any angle and still strike back with lethality. But this requirement meant creating a specialized catapult system that would eject the missile from its container using precisely controlled explosive charges. The missile would have to rise at exactly the right velocity, following a precise ballistic arc, reaching optimal altitude before its guidance systems could engage. If the velocity was too high, the missile would arc away uncontrollably, potentially tumbling end over end. Too low, and it would fall back down, crashing back onto the vehicle or into the surrounding terrain. Everything had to be calculated to perfection. The catapult itself was a marvel of engineering. A single explosive charge, carefully formulated, would have to accelerate the missile from stationary to 82 feet per second in microseconds. Not so violently that the delicate electronics inside would be destroyed. Not so gently that the missile wouldn't escape the launch environment. The pressure curve of the explosion had to be precisely shaped. The mathematical calculations required to get this right were staggering, and that was only the mechanical challenge. The missile itself had to be completely redesigned from the ground up. It couldn't use any existing Soviet missile design as a basis. None of them were suitable. None of them could withstand the crushing accelerations of a catapult launch. None of them had the right aerodynamic characteristics for vertical launch followed by a mid-flight turn. The engineers at Fakel settled on an unconventional aerodynamic layout called the canard configuration, wings in front, control surfaces in front, stabilizers in the rear. This was radically different from conventional aircraft and missile design wisdom, where the stabilizers are always in the rear and the control surfaces are integrated with the fuselage, but the canard configuration offered advantages in agility and control that would be necessary for this application. The missile would have to be extremely compact, 2 meters and 898 millimeters long, just under 9.5 feet. The body diameter, just over 9 inches, weighing only 165 kilograms, or just over 360 pounds. Inside this impossibly small package, the designers had to fit a warhead, a fragmentation warhead shaped to maximize the lethality envelope, a sophisticated onboard computer, the autopilot, electronic receivers to decode command signals sent from the ground, an antenna system to receive those guidance commands, batteries to power all of this electronics throughout the flight, a rocket motor, a solid-fueled engine that would accelerate the missile to 2,600 feet per second, or about 770 meters per second. And every single component had to be able to withstand crushing accelerations that would exceed 20 g, 20 times the force of gravity. The integration of all these components, the structural analysis, the thermal analysis, the vibration analysis that would predict how the missile would behave when subjected to the catapult launch shock, was a monumental engineering undertaking. 8 years of development stretched ahead. 8 years of sleepless nights in design bureaus, 8 years of dead ends and unexpected breakthroughs. 8 years of frustration, and occasionally despair. The integration of all these disparate technologies into a single, coherent, unified system proved to be orders of magnitude more difficult than anyone had anticipated. By 1980, the basic design had been validated. The phased array radar, the heart of the system, had been proven to work in its miniaturized form. The missile design had been finalized. The vehicle platform had been selected. The catapult system had been proven in tests, but these were only pieces. The real challenge, the overwhelming challenge, was making them work together as a unified whole. The engineers at the institutes were building something that had never been built before. They were writing the book on how to integrate command guidance, phased array radar, vertical launch capability, and autonomous operation into a single platform. Every new problem they solved created 2 new problems. More power needed for the radar meant a more powerful electrical generator. A more powerful generator meant more weight. More weight meant the suspension had to be stronger. A stronger suspension meant added complexity. More complexity meant more components. More components meant more things that could break. More things that could break meant lower reliability. Lower reliability meant the system couldn't be trusted in combat. It was a monstrous puzzle, and every single piece was dependent on every other piece. The entire system was a tightly coupled web of dependencies, where a change in one area cascaded through a dozen others. The catapult system became a nightmare unto itself. The theoretical calculations seemed fine. Fire a precisely calibrated charge of powder at just the right pressure, at just the right duration, and you would hurl the missile upward at 82 feet per second. That velocity, if perfect, would carry the missile to about 65 feet above the vehicle before gravity asserted itself and the missile began to descend. At that critical moment, the autopilot would fire the control surfaces. The missile would begin to turn. The wings and stabilizers, stored inside the launch container in a tightly folded configuration to save space, would spring open with incredible violence. Spring-loaded mechanisms, stressed to their limits, would deploy the aerodynamic surfaces. This had to happen at precisely the right moment in the missile's flight. Too early, and the springs might not have enough force to fully deploy. Too late, and the missile might have already tumbled and the deployment would be chaotic. All of this had to occur while the missile was transitioning from vertical flight to pitched over flight. While the autopilot was struggling to maintain control authority with the aero surfaces only partially deployed. While the air was still too thin to provide useful aerodynamic lift. Timing the ignition of the main rocket motor was equally critical. The main engine couldn't start too early. If it did, the missile would accelerate without having the proper orientation or altitude. The control authority would be degraded. The missile might crash. Too late, and the missile would lose altitude it desperately needed. It would fall below the optimal engagement envelope. The margin for error was almost zero. On the other side of the Soviet military-industrial complex at the Fakel Design Bureau, engineers were working on the missile itself. Every detail mattered. The warhead had to be precise, not too heavy, or the missile couldn't accelerate to the required velocity. The payload is determined by the rocket motor and the fuel budget. Add too much weight to the warhead, and the missile won't achieve its design velocity. But not too light either, or the warhead wouldn't have enough explosive material to be lethal. They settled on a fragmentation-shaped charge design weighing just under 33 pounds, capable of tearing apart an aircraft fuselage when it detonated in the right position relative to the target. The warhead had to be reliable. In combat, a failure would mean a lost target, a failed mission, or worst of all, a loss of a system and its crew. The reliability requirements were unforgiving. This wasn't a system that could be test-fired hundreds of times to prove reliability. Production would be limited, testing would be limited. The system had to be developed right the first time. It had to work correctly in its first operational deployment. Failure was not an option. During the long years of development, a parallel challenge was being addressed. The battle management computer, the system's artificial brain, had to be designed and built. For 1975, this was a formidable undertaking. Computing technology was advancing rapidly, but the state of the art was still relatively primitive by modern standards. The computers that would control the Tor system had to process radar data. They had to track up to 24 targets simultaneously. They had to assign priority values based on threat assessment algorithms. They had to communicate with the missile guidance systems. They had to manage the fire control radar. They had to oversee the entire engagement sequence from target detection to missile impact. And it all had to happen in real time. The delay between when a radar signal was processed and when an engagement order was executed could be measured in seconds. A 10-second delay in a system supposed to operate on a 2 to 3 second timeline would be catastrophic. The computer hardware had to be hardened against electromagnetic interference. Combat would expose the system to electronic warfare. Enemy transmitters would try to jam the radars. Enemy aircraft would deploy chaff and flares. Enemy cruise missiles would explode nearby. All of this electromagnetic activity would threaten to corrupt the computer's operation. The software had to be written to be absolutely robust. There were no operating systems available off the shelf. Everything had to be written from scratch. Every line of code had to be tested. Every subroutine had to be verified. The margin for error was zero. In 1983, after 8 years of development, testing, redesign, and rebuilding, the first fully integrated prototype of the Tor system rolled out onto a test range outside Moscow. The vehicle was a striking piece of engineering. It sat on tracked suspension, with 6 pairs of road wheels on each side of the chassis, for a total of 12 road wheels per track. 7 tons of steel armor protected the crew and the electronics inside. In the front of the vehicle, the driver sat in a well-protected position with an assistant beside him. The driver observed the world through reinforced viewport windows that could be quickly sealed with armor plates if the vehicle came under fire. Behind the driver and his assistant, in a slightly raised turret, sat the vehicle commander and the weapons officer. The weapons officer controlled the entire fire control system. The commander made decisions about what targets to engage and in what order. All around them, the electronics hummed with barely contained power. The detection radar, continuously spinning on top of the vehicle, searching the skies for threats. The fire control radar, built into the turret assembly, locked into its antenna, ready to track and engage. The battle management computer, processing data at speeds that would have been incomprehensible to any previous generation of military officer, running algorithms that made engagement decisions in microseconds. When the order came to go live, when the system's commander gave the order to test the entire integrated system in full combat mode for the first time, the crew went through their checklist. They had trained for this moment for years. They had studied the theory. They had run simulations. But they were about to do something that had never been done before. They were about to fire a missile from a vertical launch system mounted on a mobile platform, guided by a phased array radar over a complete command link, from a system that was supposed to be completely autonomous. The realization of what they were attempting hung heavy in the vehicle. The tension was palpable. The first tests were failures, not catastrophic failures, no explosions, no loss of control, but failures nonetheless. The electronics behaved unexpectedly. The power distribution system couldn't handle the surge of current when the catapult fired. The missile launch system worked inconsistently. Sometimes the catapult fired perfectly. Sometimes it misfired. Sometimes the missile didn't reach the right velocity. The missile's rocket engine burned erratically. The combustion chamber pressures spiked unpredictably. Some missiles achieved full thrust. Some engines burned out before reaching full power. The guidance system couldn't maintain tracking precision. The radar would lose lock on its targets. The computer would struggle to reacquire. The radar would struggle to identify small targets with confidence. The antenna array wasn't receiving data with sufficient fidelity. The signal processing wasn't working as designed. A commission was convened. The testing specialists, the manufacturers, the designers all gathered to review the results. The list of problems filled many pages. 20 issues, 30 issues. More issues were discovered with each successive test. The system was sent back for redesign. Critical components were rebuilt from scratch. The catapult system was completely redesigned. New pressure curves were calculated. New explosive formulations were tested. The missile engine was modified. Different propellant mixes were tried. Different combustion chamber geometries were tested. The computer software was completely rewritten. Every line of code was examined. Every algorithm was analyzed. Every subroutine was tested individually. The radar antenna design was modified. The number of array elements was increased. The power levels were adjusted. New cooling systems were designed. Throughout 1984 and into 1985, the work continued relentlessly. Every engineer who had worked on the Tor project was recalled. The most talented people in the Soviet military-industrial complex were focused on solving the problems. Nothing else mattered. The Tor had to work. It was too important to fail. Finally, in late 1985, after more than a year of intensive redesign and rebuilding, the updated Tor system returned to the test range. This time, the results were different. The missiles launched cleanly from their containers. The catapult fired with perfect consistency. The ballistic arcs were perfect. The missiles climbed to the optimal altitude. They turned smoothly toward their targets. The control surfaces deployed properly. The guidance commands were received and executed without hesitation. The missiles accelerated to their design velocity. They streaked toward their targets. When they detonated, when the warheads found their marks, the fragmentation warheads performed exactly as designed. They tore apart the target drones with lethal effect. The probability of kill matched the design specifications. The tests continued throughout the fall and winter of 1985. Each test brought new confidence. Each successful engagement validated years of work. By March of 1986, after 14 years from the initial concept studies, after 8 years of intensive development, after 2 years of testing and redesign, the Tor system was officially accepted into service with the Soviet Army. The decree was signed. The system was authorized for full production. The Tor was no longer an experiment. It was no longer a project. It was a weapon. It would serve in the Soviet military for decades. It would be exported to allies around the world. It would be copied by other nations. It would define an entire generation of air defense technology. To understand how this revolutionary system actually functions in combat, one needs to understand the symphony of engineering that it represents. A symphony that plays out at the speed of light and at the speed of sound simultaneously. A symphony where every note must be perfect, or the entire composition fails. The Tor moves into position. It could be anywhere. On the edge of a battlefield, protecting a mechanized column of tanks and infantry vehicles as they advance. Dug in on the outskirts of a city, defending critical infrastructure against aerial attack. Hidden in a forest, waiting to ambush low-flying aircraft or cruise missiles. Positioned at an airfield protecting the tarmac where high-value military assets are based. Once the Tor has settled into its firing position, once the vehicle has come to a stop and the crew has confirmed that the location is tactically suitable, the transition from traveling configuration to combat mode begins. The antenna on top of the vehicle, which was folded forward in traveling mode to reduce its overall height and profile, begins to rise. Hydraulic jacks pump fluid, raising the antenna assembly. The radar hardware begins to boot. The computers initialize their systems. The power generation systems ramp up to full capacity. The air cooling systems start their fans. This process takes up to 3 minutes. 3 minutes during which the Tor system is more vulnerable than at any other time. 3 minutes during which an alert enemy might attempt to strike the system with artillery or air attack. But these 3 minutes also represent the moment of transformation. A tracked, armored vehicle, dangerous in its own way, but ultimately a machine designed for transport and survival, becomes something altogether different. It becomes a hunter. It becomes a predator. It becomes an automated killing machine programmed by engineers and directed by the tactical judgment of the crew. When the final systems come online, when the antenna has fully deployed and the radar returns start displaying on the operator's screen, the Tor system is ready. The detection radar is the first system to fully activate. This is not the same as the fire control radar. This is a different system entirely, purpose-built for finding targets across a massive area of responsibility. It's a coherent pulse radar operating in the centimeter band of the electromagnetic spectrum. The detection range is approximately 17 miles, perhaps more in optimal conditions, perhaps less if the target is small or has a low radar cross-section. The antenna rotates continuously, and as it rotates, it sends out radio waves at a specific frequency. These radio waves bounce off any object that is large enough to return a signal. An aircraft, a helicopter, a drone, a cruise missile, a ballistic missile in the terminal phase of its flight. All of these objects reflect radio waves. When those electromagnetic reflections return to the radar antenna, they are processed by the receiver. Distance is calculated from the time delay between transmission and return. Bearing is calculated from the angle at which the signal was received. Altitude is estimated from the Doppler shift in the returning signal. The Doppler effect is the shift in frequency that occurs when a radar wave reflects off a moving object. An object moving toward the radar returns a higher frequency. An object moving away returns a lower frequency. From this frequency shift, the radar calculates whether the object is approaching or receding, and at what speed. As the detection radar scans the skies approximately every 3 seconds, a new snapshot emerges, an updated three-dimensional picture of everything that is flying within its detection range. Built into this detection radar system is another critical system called friend or foe identification. The radar sends out a special coded signal. If the object receiving that signal is a friendly aircraft, equipped with the proper identification transponder, it automatically sends back a coded response at the correct frequency. This happens at light speed. In less than a microsecond, the system knows whether what it is looking at is a threat or a protected asset. When the detection radar locks onto something that doesn't respond to the friend or foe query the way it should, when it detects something that is unidentified, something that refuses to identify itself, something that is actively evading the identification system, something that is clearly hostile, the battle management computer takes note. That contact is flagged as potentially hostile. Within 3 seconds, the detection radar rescans the area where the suspicious contact was detected. It confirms. The contact is real, the contact is still there, the contact is moving. The computer continues to process the radar returns, and within moments it makes a critical determination. It analyzes what the contact is. Is it a fighter? Is it a cruise missile? Is it a drone? It determines what the contact is doing. Is it flying level? Is it climbing? Is it descending? Is it turning? It calculates where the contact is heading. Is it approaching the Tor? Is it moving parallel? Is it receding? The battle management computer, this artificial brain of the system, can simultaneously track up to 24 different targets. 24 aircraft, or missiles, or threats, all being followed at the same time. As it tracks each target, it assigns priority values. The fastest movers are prioritized because they are the most dangerous. Threats moving at supersonic speeds get the highest priority. Targets approaching the Tor are prioritized over targets moving away. A threat that is coming toward the defensive position is more dangerous than one that is leaving. Targets at altitudes where they can actually threaten the system are prioritized. A high-altitude bomber flying at 30,000 feet might be a threat, but not an immediate threat. A low-flying cruise missile at 500 feet is an imminent threat. Within the space of a few seconds, the computer has made decisions about what matters most. What is the most dangerous threat? Which target represents the highest probability of successfully striking the Tor? The information is passed to the weapon system. The turret rotates. The motors begin to turn the entire fire control radar assembly. The phased array antenna and the 8 missile launch canisters mounted around it begin to point toward the assigned target. Now comes the most sophisticated part of the entire system. The targeting radar, the fire control radar. This is not merely a radar that detects. This is a radar that engages. This is where the phased array technology that the Soviets had struggled so hard to miniaturize comes into play. This antenna array represents the cutting edge of what was possible in the 1980s. The phased array antenna, just meters in size, contains thousands of individual antenna elements. Each element can be independently controlled. By adjusting the relative phase of the signal sent to each element, the radar beam can be electronically steered without any mechanical movement whatsoever. The antenna is mounted on top of the Tor turret, directly above the 8 launch canisters. The phased array operates in the centimeter band, sending and receiving signals at frequencies that are optimal for detecting small targets like aircraft, missiles, and helicopters. The fire control radar acquires the target that the detection radar has designated. It locks on. The antenna beam focuses on that specific point in space. Electrons flow through the transmission lines. Electromagnetic waves emanate from the antenna array. The waves reach out across the sky toward the target. When those waves strike the target, when they illuminate an aircraft flying toward the Tor, they reflect. The reflected energy returns to the antenna array. The receiver detects this reflected energy. The radar measures the strength of the return. A strong return means the target is close. A weak return means the target is at the maximum range. The radar measures the Doppler shift. It measures the rate of change of Doppler shift, which gives the radar information about the target's acceleration. Is it turning? Is it climbing? Is it descending? From this information, the radar computes the target's trajectory, the target's velocity, the point where it is heading. The fire control radar is locked onto the target on 3 axes simultaneously. Azimuth, the side-to-side position; range, the distance to the target; elevation, the up and down position. The radar operator on the Tor, the weapons officer, sits in front of a display that shows all of this information: the target position, the target velocity, the target classification, all in real time. When the weapons officer confirms that this is indeed a hostile target, when the commander makes the decision to engage, the weapons officer presses the firing button. Then happens something that defies intuition, something that seems almost impossible. The portholes explode with fire. A carefully calibrated explosive charge in the launch canister detonates with tremendous force. The missile is accelerated from 0 to 82 feet per second in a fraction of a second. The acceleration is violent. The missile experiences crushing G forces. The shockwave travels through the missile's structure. The internal components are compressed. The warhead is pressed backward. The fuel in the rocket motor sloshes under the extreme acceleration. The missile clears the launch canister. It has perhaps 2 meters of clearance before it reaches the end of its ballistic flight. For 2 seconds, the missile is in free flight. It is rising on its momentum. Gravity is pulling it down, but it is still climbing. At approximately 65 feet above the launch vehicle, the missile reaches its apogee. For just an instant, it hangs in the air. Its vertical velocity becomes 0, and then gravity wins. The missile begins to descend. But in that instant of transition, the onboard autopilot system becomes active. Signals are being transmitted from the ground-based fire control radar. The radar is tracking both the missile and the target. The computer on the ground is calculating the error between where the missile is and where it needs to be. The computer is calculating the error between where the target is and where the missile is aimed. The computer is sending command signals to the missile. Correct left, correct right, correct up, correct down. The signals flow from the Tor's antenna to the missile's receiver. The autopilot receives the correction commands. It processes them. It controls the missile's control surfaces. As the missile transitions from ballistic flight to powered flight, as it reaches the top of its arc and begins to descend, explosive actuators deploy the folded wings. Springs under tremendous tension release their energy. The wings snap open. They deploy in less than a second. Once deployed, the springs are jettisoned. They fall behind the missile. They would only create drag and interfere with flight if they remained attached. The canard control surfaces, the wings in front, deploy. The fuselage and the wings of the missile shift its center of pressure. The aerodynamic forces acting on the missile suddenly change. The autopilot has to compensate. The missile was designed for this. The aerodynamic design accounts for these changing forces. As the missile pitches over, as it transitions from vertical to horizontal flight, The autopilot commands the rocket motor to ignite. The rocket motor is a solid fuel design. The combustion is nearly instantaneous. The fuel burns with tremendous intensity. Hot gases accumulate in the combustion chamber. Pressure builds. The gases escape through the rocket nozzle at the rear of the missile, expelling at supersonic velocities. Thrust is generated. The missile accelerates. At a distance of about 1.5 kilometers from the launch vehicle, the missile reaches its design velocity, 2,600 feet per second, 770 meters per second. The missile is now traveling at approximately 5,400 miles per hour. Throughout this entire sequence, the fire control radar continues to track both the missile and the target. The antenna beam electronically steers. The radar measures the position of the missile. The radar measures the position of the target. The ground-based computer calculates the error. The computer calculates the guidance commands needed to correct the missile's trajectory. The commands are transmitted. The missile's receiver decodes the commands. The autopilot executes the guidance commands. The control surfaces adjust. The missile's trajectory is corrected. This process happens continuously. Every few milliseconds, new measurements, new calculations, new guidance commands. This is command guidance. It is the opposite of fire and forget. The missile doesn't know how to get to the target. The missile doesn't have an inertial navigation system that will guide it autonomously. The missile is a dumb projectile. It is smart only because the ground station is making it smart. The ground station is providing the intelligence. The ground station is correcting the trajectory in real time. The Bordovaya, the onboard battle management computer of the missile, is simple by design. Its only job is to execute the commands that come from the ground. Adjust the control surfaces by this amount. Fire the rocket motor now. Detonate the warhead now. Simple commands, but commands that must be obeyed instantaneously. The missile streaks toward the target. The target, if it is an aircraft, might be maneuvering. The aircraft might be turning. The aircraft might be climbing or descending. The aircraft might be deploying countermeasures, chaff clouds, metal strips cut to specific lengths that confuse radar, flares, burning magnesium devices that distract infrared seekers. But the command guidance system is not confused by these countermeasures. The ground radar is locked onto the target. The radar is measuring the actual position of the aircraft. The countermeasures create false returns on some radars, but not on this one. The Tor's fire control radar is sophisticated enough to distinguish between the real aircraft and the chaff clouds. The guidance continues. The missile closes the distance. 10 kilometers away, 5 kilometers away. The target is filling the radar beam now. The radar returns are strong. The range is closing rapidly. 2 kilometers away, 1 kilometer away. The missile is 50 meters away, 25 meters away. The warhead proximity fuse becomes active. The proximity fuse is the key to lethality. Instead of hitting the aircraft directly, which is difficult because aircraft are small and moving targets, the warhead detonates when the missile passes near the aircraft. The proximity fuse uses radar. When the radar emitted from the missile's antenna detects that it is very close to a large metallic object, when the return signal strength exceeds a threshold. The proximity fuse commands the warhead to detonate. The explosion tears the warhead apart. Fragmentation is achieved. Thousands of metal particles traveling at hypersonic velocity radiate outward. These fragments are lethal. An aircraft, when struck by this fragmentation pattern, will suffer catastrophic structural damage. Hydraulic systems will rupture. Fuel lines will be severed. The airframe will be penetrated. Control surfaces might be damaged beyond the pilot's ability to maintain control. Engines might be damaged. Engines might catch fire. The aircraft might become unflyable. The aircraft might crash. The employment of the Tor system, the process of taking a hostile target from initial detection to final engagement, typically takes place over 4 to 7 seconds. 4 to 7 seconds from the moment that the detection radar first locks onto the threat to the moment the warhead detonates. For a Tor equipped with multiple missiles, with 8 missiles on the launch vehicle, the system can engage another target while the first missile is still in flight. A second missile can be launched, then a third, then a fourth. If the Tor is sufficiently supplied with missiles, if a transport vehicle has recently resupplied the launcher, the system can engage up to 8 different targets in rapid succession. Each missile follows its own trajectory. Each missile receives its own command guidance. Each missile is tracked by the radar. The radar antenna beam electronically scans among all the targets and all the missiles, dividing its time. A few milliseconds for target 1, a few milliseconds for target 2, a few milliseconds for missile 1, a few milliseconds for missile 2. The time sharing happens so rapidly that all of the engagements appear to be simultaneous. This is the power of the Tor system. This is why military planners around the world were so terrified of it. A single Tor vehicle could defend against a coordinated air attack involving multiple aircraft or missiles. Once the 8 missiles have been expended, once all of the launch canisters on the turret have been emptied, reloading is required. A transport and reload vehicle, one of the support vehicles that accompany the Tor in the field, moves into position. The transport vehicle is equipped with 4 additional launch canisters containing 4 additional missiles. The canisters are swapped out. The depleted canisters are removed from the turret. Fresh canisters are installed. The process takes approximately 18 minutes. 18 minutes during which the Tor is completely defenseless. 18 minutes during which the system cannot fire. This represents a significant vulnerability. In a high-intensity combat situation, in a scenario where the Tor is under sustained attack from multiple air threats, 18 minutes is a lifetime. But the Tor was not designed for such scenarios. The Tor was designed to protect advancing mechanized columns, to defend against the occasional hostile aircraft, to defend against cruise missile attacks, to defend against surprise air attacks. The philosophy behind the Tor was that the system would operate within a larger air defense network. The Tor would handle short-range threats. Medium-range systems would handle threats that were further away. Long-range systems would engage threats that were even more distant. The Tor would not fight alone. But if it had to, if the network broke down, if it found itself alone and besieged, the Tor was fully autonomous. It could track and kill multiple targets. It could respond to threats from any direction. It could engage without external communication. It could survive. But survival alone is not victory. In the 1980s, and the years after the Tor was first accepted into service, Soviet military planners understood that they had achieved something remarkable. They had built the most advanced mobile air defense system in the world. Nothing comparable existed in Western arsenals. The American Patriot system, the premier air defense system of NATO, operated on different principles. The Patriot used semi-active guidance. The ground radar illuminated the target continuously while the missile flew. The missile's seeker rode along on that radar illumination and guided itself. The Tor used command guidance. The ground station calculated the guidance commands and transmitted them to the missile. Both approaches had merits. Both approaches had drawbacks. But in the realm of low-altitude engagement, in the role of defending mechanized columns against aircraft and helicopters, the Tor was superior. By 1986, however, even as the Tor was being accepted into service, even before the first systems reached the troops, Soviet designers were already thinking about the next evolution. Military technology never stands still. The moment a new system enters service, the moment it proves its worth, military planners begin to think about how to make it better. What weaknesses does it have? What vulnerabilities can be exploited? What enemies are developing? What countermeasures will be necessary? In 1987, approximately 1 year after the Tor was accepted into service, design bureaus began preliminary studies of how the system could be modernized. The baseline Tor had been a success. But there was no such thing as a perfect system. The radar could be jammed. The fire control system had limits. The missile range was limited. The missile size was limiting the amount of explosive payload. The vehicle's mobility could be improved. The question before the designers was how to address these limitations without completely redesigning the system. The upgrades that would define the Tor-M1, the modernized version, were radical. The chassis was completely redesigned. The new chassis, designated the GM5955, was heavier and more powerful than the original. 7 road wheels per side instead of 6, greater ground clearance, better suspension. The vehicle weighed 37 tons, 5 tons heavier than the original. But the added weight was justified. The new electronics and the new systems that would be installed demanded more structural strength. The turret was completely redesigned. The new turret could accommodate upgraded electronics. The radar systems were completely redesigned. The detection radar was significantly upgraded. It could now simultaneously track up to 48 different targets instead of 24. The signal processing was completely rewritten. A new 3-channel signal processor was designed that could better handle electronic countermeasures. If an enemy began to deploy passive countermeasures, if they scattered dipoles or other radar-reflecting chaff, the upgraded radar could automatically filter out these false returns. The operator wouldn't be confused. The system wouldn't lose track of the real target. The fire control radar was also upgraded. It became more sensitive. It could now automatically track smaller targets. A video optical channel was added. A television camera with an optical tracker could help the system maintain lock if the enemy attempted to jam the radar. The missile was upgraded as well. The new 9M331 missile was designed to be compatible with the new launcher system. It was almost identical in mass to the original missile, 167 kilograms. But subtle improvements were made throughout. The rocket motor was upgraded. The fuel was changed to provide more consistent performance. The autopilot was upgraded, better control authority, faster response times. The missile could reach 850 meters per second, 50 meters per second faster than the original. The engagement range increased. The missile could now engage targets up to 25 kilometers away. The engagement altitude ceiling increased to 10 kilometers. The accuracy improved. The probability of kill against a fighter aircraft increased from a range of 0.26 to 0.7 for the baseline system to 0.45 to 0.8 for the Tor-M1. Against helicopters, the probability of kill increased from estimates of 0.4 to 0.6. Against cruise missiles, the system became phenomenally effective, achieving probabilities of kill in the range of 0.6 to 0.75. But the single biggest improvement was in the crew ergonomics and system automation. The original Tor required 4 crew members: a driver, a driver's assistant, a commander, a weapons officer. The Tor-M1 reduced crew requirements to 3. The vehicle could operate with just a driver, a commander, and a weapons officer. How was this possible? Automation. The new computerized systems, built around advanced processors of the era, could handle many of the tasks that previously required a dedicated operator. The system could automatically detect threats. The system could automatically classify threats. The system could automatically alert the crew if a threat was identified. The system could work with multiple fire control radars on the same target or on different targets. In 1989, the upgraded Tor-M1 system went into testing. The results were outstanding. Every specification was met or exceeded. In 1991, after the collapse of the Soviet Union, the Tor-M1 was officially accepted into service with the Russian Federation's armed forces. The modernization didn't stop. By the early 2000s, design bureaus were already working on an even more advanced version. The Tor-M2 would represent a quantum leap in capability. The Tor-M2 would incorporate technologies that had seemed impossible just years earlier. The new missile, designated the 9M338, was the centerpiece of this upgrade. The 9M338 was in many ways a complete redesign. The engineers recognized that by reducing the missile's weight slightly, by optimizing every aspect of its design, they could increase the number of missiles that could be carried on a single vehicle. The 9M338 weighs 163 kilograms, only 4 kilograms lighter than the previous missile. But this small reduction in weight opened incredible possibilities. The new launch containers, designated the 9M281 transport launch canisters, were redesigned to accommodate 4 missiles instead of 2. This meant that a single vehicle could now carry 16 missiles, twice as many as the baseline Tor, twice as many as the Tor-M1. 16 missiles ready to fire, 16 engagements, 16 targets that could potentially be destroyed before the vehicle ran dry. The new canisters were mounted in 2 groups of 4 on opposite sides of the turret. The modular design meant that transport vehicles could bring new, complete sets of canisters. The depleted canisters could be swapped out wholesale. The reload process could potentially be accelerated. The new rocket motor for the 9M338 burned at higher efficiency. The missile could achieve 1,000 meters per second, 350 meters per second, faster than the Tor-M1. The engagement range extended to 52,000 feet, 16 kilometers. The engagement altitude ceiling doubled from 10 kilometers to 20,000 feet, 12 kilometers. The missile was designed with hardened electronics to resist jamming. New countermeasure rejection algorithms were incorporated into the command guidance system. The missile had a far greater ability to defeat electronic warfare attempts. When the 9M338 missile was finally ready, when the first production examples were built, the engineers and planners understood that they had achieved something remarkable. The Tor-M2 system had double the missile capacity of any previous version. It had double the engagement altitude of the baseline Tor. It had twice the range. It had radically improved target acquisition and tracking. But the enhancements didn't stop with the hardware. The computer systems were upgraded again. Multi-processor architectures replaced single processors. The battle management computer could now simultaneously engage 4 different targets, not sequentially, not time-sharing the radar beam among 4 targets and 4 missiles, but truly simultaneously engaging 4 different targets. The radar antenna, now even more sophisticated, could track additional targets while simultaneously guiding 4 missiles. The system achieved engagement rates that seemed to defy the laws of physics. 2 missiles could be launched with as little as 3 to 4 seconds between launches. The engagement sequence was streamlined. The detection system could track a larger number of targets than ever before. If you could see the target, you could engage it. By 2009, design bureaus announced that a further evolution was being considered, the most ambitious upgrade yet. The Tor-M2 would eventually be equipped with even more advanced components. Not just evolutionary improvements, revolutionary capabilities. The optical television channel that had been an accessory on the Tor-M1 became increasingly important. In an electronic warfare environment where radar might be jammed, the optical system provided a backup. The system could track a target using television. Once locked onto an optical image, once the camera had acquired the target, the system could maintain engagement. The targeting computer would command the missiles to fly toward the last known position of the target. The missile, in the absence of command guidance, could rely on its own optical seeker or its own logic to accomplish the intercept. By 2016, the Tor-M2 with the new 9M338 missile was officially accepted into service. The Russian Federation now possessed an air defense system that operated across an unprecedented range of altitudes, from 10 meters, low enough to threaten helicopters hovering over a battlefield, all the way to 12 kilometers, high enough to threaten medium-altitude reconnaissance aircraft, from 1 to 16 kilometers of range, from engagement of single targets to simultaneous engagement of 4 different targets. And crucially, The system had been designed with something in mind that the original Tor was never truly tested against: small targets, drones, unmanned aircraft, reconnaissance drones, unmanned combat vehicles. The detection radar of the Tor-M2 was sensitive enough to detect these small targets. The system could track them. The system could engage them. Whether to actually fire a $1 million missile at a $10,000 drone was a tactical decision for the crew, but the capability existed. The system could see them. The system could kill them. And that capability alone had enormous value. In reconnaissance operations, knowing that something can see you, that something can kill you, is enough to change behavior. Pilots will fly differently if they know they can be detected. Drones operators will change their patterns if they know their vehicles can be seen. Fear is a powerful motivator. The Tor inspired fear. Throughout the early 2000s and into the 2010s, the Tor-M1 and Tor-M2 systems were being exported. Russia's military industries were marketing the system to allies. The system found buyers in Greece, in Iran, in China, in other nations. Each nation that purchased the Tor understood that they were acquiring not just a weapon, they were acquiring a piece of cutting-edge military technology that was competitive with the best systems that the West had to offer. But there was an unexpected development. The designers wanted to explore new configurations. Instead of mounting the system on tracked vehicles, what if the entire fire control module could be removed from the vehicle and mounted on something else? What if it could be mounted on wheels? Wheeled vehicles offered certain advantages. They were cheaper to produce. They were cheaper to operate. They had faster mobility on roads. Some nations preferred wheeled systems. So engineers developed the Tor-M2E, an export variant mounted on a 6x6 wheeled chassis. The Tor-M2E retained all the capabilities of the tracked version: 16 missiles, the full radar suite, the full automation and target tracking. The only difference was the platform it rode on. But this opened even more possibilities. What if the entire fire control module could be mounted separately? What if it didn't need to be on a vehicle at all? What if it could be mounted on a trailer? What if it could be mounted on a stationary platform? In 2013, something remarkable happened. The Tor-M2KM, a modular variant, completed testing. This was not mounted on any vehicle. This was a complete fire control system mounted on a platform that weighed just 15 tons. The entire combat power of a Tor system, all of the radars, all of the missiles, all of the automation and intelligence, packaged into 15 tons. This module could be mounted on a large trailer. It could be hauled by any truck capable of pulling heavy cargo. It could be towed to a location. It could be set up and made operational within hours. The modular Tor-M2KM could protect airfields. It could protect ammunition depots. It could protect command centers. It could protect any valuable installation. It could be moved by helicopter. A heavy lift helicopter could carry the entire fire control module to a location where no vehicle could reach. It could even be mounted on top of buildings. A city building could be converted into an air defense platform. The fire control module could be lifted to the roof by a crane. The module would provide complete air defense for that location. All of the detection and engagement capability of a full Tor system, but stationary, protected by building walls and roof. The significance of this development cannot be overstated. For decades, air defense had been the domain of mobile systems, systems that had to travel with the army, systems that had to keep up with mechanized columns. But the Tor-M2KM demonstrated that air defense didn't have to be mobile. It could be fixed in place, it could be hidden, it could be distributed. An enemy would have to search for these hidden modules. The modules could be spread across a wide geographic area. Multiple modules could be linked together, sharing targeting information, creating a sophisticated integrated air defense network. The philosophy behind the Tor system, the principle that had guided its development from the very beginning, was autonomy. Every system should be able to operate independently if necessary, but systems should also be able to network. The baseline Tor was autonomous. The Tor-M1 could share information with other air defense systems. The Tor-M2 had even more sophisticated networking capability. By 2024, as this narrative is being presented, the Tor system has been in service for more than 3.5 decades. 38 years of continuous service, 38 years of evolution, 38 years of refinement. The original concept, born in the minds of Soviet engineers in 1975, has survived and thrived through the collapse of the Soviet Union, the transition to the Russian Federation, the development of new threats, the emergence of new technologies. The Tor has adapted. New modernization programs are ongoing. New missiles are being tested. New radar upgrades are being developed. The story of the Tor system is not finished. It continues into the present day and will continue into the future. The very first meeting, where Soviet engineers discussed the concept of the Tor back in 1972, had one person asking a critical question. How can we build an air defense system that can see through deception? How can we build a system that the enemy cannot jam? How can we build a system that can operate alone if it has to? 50 years later, That fundamental philosophy still guides the development of the Tor. Autonomy, reliability, the ability to function in an electronically hostile environment. The Tor was never meant to be a perfect system. No military system is perfect. The Tor was meant to be a system that could do the job, a system that could protect, a system that could engage, a system that could survive. And in all of these measures, the Tor has succeeded beyond the expectations of its designers. When Veniamin Pavlovich Efremov, the chief designer, first put his vision on paper in 1975, he probably never imagined that his creation would still be in production and evolution a half-century later. He probably never imagined that his system would terrify the skies. He probably never imagined that so many air forces around the world would regard the Tor as one of their most potent threats. But he did imagine one thing. He imagined that by building a system around solid engineering principles, around technologies that were proven or nearly proven, around a design philosophy that emphasized reliability and autonomy, he could create something that would endure, something that would survive, something that would be improved and enhanced and modernized, something that would remain effective for decades. Veniamin Pavlovich Efremov was right. The Tor system stands as a monument to Soviet engineering at its finest. It stands as proof that brilliant minds, working with resources and determination, can accomplish remarkable things. The Tor took 14 years from concept to operational service. It has now been in service for 3 times that duration. 14 years of development, 42 years of operational service. And it continues. The Tor system teaches us something profound about military technology. It teaches us that a well-designed system, one that addresses real problems, one that is built on solid engineering principles, can have staying power. The Tor addresses the problem of air defense in an electronically hostile environment. It does this through the application of phased array radar technology. It does this through the integration of multiple sensors. It does this through the application of autonomous decision-making. These are not tricks or shortcuts. These are fundamental approaches to solving a difficult problem. The Tor also teaches us about the process of military development. It took longer than anyone expected. The first tests failed. The system had to be completely redesigned. There were moments when success seemed impossible. But the commitment was there. The expertise was there. The resources were committed. And in the end, it worked. The Tor is not perfect. It has limitations. It can be overloaded with simultaneous attacks. Its missiles can be defeated by well-executed electronic warfare. Its short range, relative to longer-range air defense systems, means it protects a limited area. But perfect systems don't exist. The Tor is an excellent system. It is a proven system. It is a feared system. And it continues to evolve. As military technology moves forward, as threats change, as new weapons emerge, the Tor will continue to be modernized. New missiles will be integrated. New radar technologies will be incorporated. New networking capabilities will be added. The Tor will adapt and survive. The story of the Tor system, from its conception in 1972 to its operational deployment in 1986 to its current service in 2024, is a story of engineering excellence. It is a story of human determination. It is a story of what is possible when brilliant minds work together toward a common goal. The sky above every battlefield where a Tor system is deployed is contested. That sky belongs to whoever is most skilled. But make no mistake, the Tor is a serious competitor for control of that sky. And pilots around the world know it.